हेलो बच्चों, सत श्री अकाल and namaste from my side. How are you all? Right. So again we are back, right, with the chapter of electromagnetic induction, right, with the chapter of electromagnetic induction. So guys, it's gonna be like, right, slowly we are going to, right, post up all of those chapters, right, and especially you all are aware of, for this batch we are right following the reverse engineering. Reverse engineering, it means that into very less amount of the time, very high efficiency, okay, into the very less amount of the time of 55 minutes or 1 hour, right, through the PYQs we are seeing the theory of the entire chapter. Okay, so we are covering the PYQs also and we are seeing the theories of the entire chapter also. Okay, so this is what we are following, okay, like the same, okay, from the different organization, from different this one, the examinations, right, the questions are going to come. Okay, so let's not waste the time and be prepared for that. Okay, we are going to move forward into the questions of the electromagnetic induction. Okay, so the agenda of today's session, right, will be what? The electromagnetic induction practice question. Okay, so let's move on to it. The first sum appears on your mobile and the computer screens, right? The first sum appears. Okay, this is a very awesome sum. Okay, asked in JEE Main 2013. JEE Main 2013. A metallic rod of length L is tied to a string of length 2L. There is one string of length 2L and the metallic rod of length L, they are both tied together with respect to a point. Okay, now both of them are rotating with an angular velocity omega. So both are rotating. This is a rod, this is a string attached. They both are rotating with an angular velocity omega around a point. Now, if there is a vertical magnetic field in that region, the EMF induced across the rod will be what? Vertical magnetic field, it means like, suppose we are having the magnetic field like this way, right? This is a situation of the vertical magnetic field, right? Crossing up the desk, okay, crossing up like this way. Then what happens? Okay, what happens? Now, what we have to calculate? We have to calculate the EMF across the ends of the rod. See, the general formula we have discussed into the previous lectures, the third lecture. Okay, this is the general formula to calculate the EMF. Into the case of the rotation of the rods we have discussed. Okay, how we are going to use that general formula, I am going to show you up. Okay, don't get worried, but first of all, let's give you all a minute to solve this question. Okay, so this is a minute. Come on, everyone, try and select the correct answer. Come on. Okay, I think 5 seconds are about to remain. It's a very simple question and we are going to learn that part. Okay, now see what actual the situation states. Okay, the situation states that this is a string of length 12, right, and this is a rod, right, of length they are hinged at this point, right? They are hinged at this point. Now entire system is getting rotated with an angular velocity omega. Right. Now suppose if the question states that if we are having the vertical magnetic field, right? So first of all, if velocity and the magnetic field are perpendicular to each other, right, then and then we are going to have an EMF. So here, magnetic field is in this direction, the velocity is in this direction, right? Obviously, they are perpendicular to each other. It means one thing is fixed. Yes, we are going to have the EMF across the two ends of the rods, right? See, whenever this kind of the questions comes up in front, na, just check it out. The first step is to check it out, right? Whether the velocity is perpendicular to the magnetic field or not. If in case if it is not perpendicular, because why? See, the main formula of the EMF, it is right, B V L sine of theta. If B and V, they both are perpendicular to each other, then and then this theta is going to be 90 degree, right? Okay. If they are going to be the parallel or anti-parallel, then immediately this EMF across the rods will be zero. EMF across the rods will be zero. Okay. So the first thing that we have to take care, right, is to check it out whether what is an actual angle between the velocity and the magnetic field. So here the angle between the velocity and magnetic field would be 90 degrees. So here there are chances are there. I must not say chances are there, but yes, EMF will be produced in between the two ends of the rods. Now, what was the actual formula? The general formula we discussed for the general formula, right? We discussed for this, right? It was EMF is equal to integration of B omega, right? L of dx. This will be the limits of the integration. Right? This will be the limits of the integration. You can say dx or you can say it as a dl. Right. So this was a general formula. Now, what will be the limits of the integration? I told you all the hinged point would always be 0. In the lecture, I told you the hinged point will always be 0. Now, the rod, the first end of the rod is A, the second end of the rod is B. The A edge of the rod is situated at the distance 2L. The B edge of the rod is situated at the distance 3L. Now we need to calculate the potential difference between the points A and B, right? So it means this L1 and L2 are going to replaced by, right? This L1 and L2 are going to replaced by A and B, right? Similarly, right, this A and B, if I'm going to just check it out, right? So can I say it as it is the limit will be from 2L to 3L. With respect to 0, the first step, the edge of the rod is at the 2L. With respect to the 0, right, the second edge of the rod is at 3L. So whatever the limits of the integration we are placing up, it is between the 2L and 3L. Right. So EMF of the rod, that is equal to B omega L. So can I say it is B omega L square by 2, right, limiting from 3L, right, to 2L, right. Okay. So calculating this, will be 9 minus 4. So it is 5 B omega L square by 2. This will be the EMF produced in between the two ends of the rods, right? This will be the EMF, right, produced in between the two edges of the rod. Okay. So guys, this is a general formula that all the time we have to take care of. Okay. The general formula all the time that we have to take care of, right? Suppose if the situation is saying that, right, calculate the potential difference between this point and there's a midpoint of the rod and the edge, right? Again, we are having the same solution. We have to just replace the limit. Okay. Again, if someone says find out the in between the, right, this is not so possible. In between the any 2 points on the rods, suppose if we want to calculate the EMF, right, the motional EMF, or you can say the potential difference, okay, then you have to just think about the limits of the integration, right, limits of the integration. So phi B omega L square by 2, this will be the perfect answer to this specific question, right? Phi b omega L square by 2 will be the perfect answer for this specific question. Okay. Now, I'm moving aside on the countdown of 5 seconds. If you want to just note this down, you can. 5, 4, 3, 2, 1. You might have paused the video and did that. Next question. Now, this question is completely based on the LR circuit. Before moving on to this question, it is important to understand what actual the LR circuit is all about and what kind of the situation arises within it. Right now, if I am going to discuss the question first, right, then it would be crucial. If I'm going to discuss this theory, and then immediately we're going to discuss the question, then the things are going to get sorted. Okay. Now, suppose we are having one circuit. This inductor, this is resistor. It is connected. This is a key. DC supply, right? This is L, this is R. The current into the circuit is this, and this we are having di by dt. The rate of the change of the current is di by dt. Okay. Now, LR circuit, whenever the DC supply is connected to the LR circuit, first step, okay, DC supply, it is given to LR circuit. Into the upcoming chapter, we are going to see how the AC supply is given to the circuit and things are going to get changed. What is the difference between the AC and DC supply? Lots of things we are going to discuss, right? So first step is, now LR circuit is basically having 3 stages. The first one is an initial stage. The second one is a steady state, right? And the third one is a transient state. Right? Initial state, steady state, transient state. Right? Initial state, steady state, and transient state. Right? The moment at which switch is closed, T is equal to 0. That is initial stage, right? At T is equal to 0, key is closed, right? This stage, it is known as the initial state. Okay, now we have seen this part into the simulation. Okay, we have seen if we are replacing the inductor and only resistor is present into the circuit, then the current flowing within it is constant. But suppose if inductor is introduced, right, and in the initial stage switch is closed. When switch is closed, inductor is going to offer the highest amount of the resistance and going to store the maximum amount of the energy. For the very short period of the time, the current flowing into the circuit will be low value. Till the amount of the time the inductor is going to gain the entire energy, slowly charges will move. Now, when after a very long amount of the time, when the inductor is gone, it offers the zero resistance and slowly, or in some cases gradually the current is increasing. So as of that reason, we are having the rate of the current flow as di by dt. So the first one is an initial stage. The second one is a steady state. Steady state, it means that, right, at infinite time, after very long amount of the time, the inductor offers the zero resistance. So in that case, only R is active, the resistor is active. But after a very long amount of the time, only the resistor is active into the circuit. And the third state is a transient state. It is in between t is equal to 0 to t is equal to infinity. So initial stage t is equal to 0, very long time, steady state, right? Okay, and the transient state, it is in between initial and the steady state. Whatever the things moves on, right? Whatever the things moves on, it moves on in between the initial and steady state, that is the transient one. Right? Initial and steady state, that is a transient one. Now, the same circuit I am talking about, transient state. The first is rise of the current. I told you all, na? First of all, the inductor is not connected. Only resistor is connected and the current flowing through the circuit is constant. Now, suddenly if the inductor is connected, right, initially when it is connected, the flow of the charges will be at the very low value. The flow of the charges will be at the very low value, right? Okay, and slowly the rise of the current will take place. Now, how it is going to be take place? Suppose if E is given to the circuit, right, and we are applying the Kirchhoff voltage law, right? We are applying KVL to the circuit. Right? If we are applying the KVL to the circuit, then what happens? E minus I of R, that is equal to L di by d of t. Right? Okay. So here L di by d of t is equal to E minus I of R. So di is equal to E by L minus IR by L, right? Okay, into dt. Integrating this and following some steps, we are going to have, right, the rise of the current. It means that what would be the mathematical expression to represent the rise of the current into the LR circuit? What will be the mathematical representation, right, to like what will be the mathematical expression to represent the rise of the current into the circuit? So that would be I is equal to I0 1 minus e to the power by tr by L, right, where t is equal to L by R, which is known as time constant of the circuit, right? Somewhere it is also known as tau, right? So my question is, an explanation is, inductor was not there, current flowing into the circuit was constant. Inductor is connected, immediately inductor is going to store the maximum amount of the energy. The amount of the time the inductor is taking to store the energy, right? For the same amount of the time, the current will slowly increasing its value. Now what happens? The current is rising. Because inductor is, see, slowly inductor is storing its energy. So from infinite resistance, its resistance value is also decreasing to 0. Why? Because into the steady state we saw, at the infinite time, inductor is going to give all the 0 resistance and only resistor will be activated. Right? So this is the formula of the rise of the current into this circuit. How the current is rising, it is represented by this mathematical expression. Now, things are gonna get, current got raised. Okay, now what I want to do, I want to disconnect the battery and want to check it out the decay of the current. Okay, this is the entire process. Now battery is disconnected. Right, and we are going to check it out the decay of the current. Right, we are going to check it out the decay of the current. Okay, how we are going to check that part? Okay, how we are going to check that part? The decay of the current will be, Okay, see, decay of the current, it means that now source is disconnect and we are applying the KVL. Source is, battery is disconnected, so applying KVL, right, we are going to get I of R minus L di by dt, that will be equivalent to 0. So di by dt, that is equal to I R by L, right? So integrating this, you are going to have I is equal to I0 e raised to minus t R by L. This is the expression by which current is decaying, right? For the decay of the current, it is compulsory that battery should be disconnected, right? Battery should be disconnected. Okay, so this is the most important stuff that we have seen. Okay, so this is what the actual all of those things about the LR circuit. It is only depending on the three stages. The first one is an initial stage, the second one is a steady state, and the third is a transient state. So whatever the things are going on into the transient state only, right? Okay, rise of the current, decay of the current. I'm moving aside. If you want to just pause this video, I'm giving you all the time. Okay, you can just pause this video and scroll it up. Come on, everyone. You can just note this down, right? 9 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. That's it. Okay. Now we are going to come back to this sum. In the circuit shown here, the point C is kept connected to the point A. Point C is kept connected to the point A, right? Till the current flowing through the circuit becomes constant. Till this current flowing through the circuit becomes constant, it means they are talking about the infinite time, right? Till the circuit becomes steady, right? Till the circuit becomes steady. Okay, now afterwards suddenly C is disconnected from the point A and connected to the point B at time t is equal to 0. Ratio of voltages across the resistance of inductor and the resistor will be what? The question is of JEE Main 2014, right? The question is of JEE Main 2014. Okay, very awesome question it is, right? We have seen this into the LR circuit. Don't get worried, again we are going to check it out, but first of all, let's give you all a 1 minute, right? Right now, yeah, suppose I'm talking about a time when A is connected to C, right? Or suppose I'm talking C, suppose if A is connected to C, then battery is disconnected, right? The source is connected. Okay, now when this connection gets break out and B is connected to C, right, it means that the source is removed. Okay, it means that source is removed. Sorry, Okay, see, connection of B with C means source is removed. So first of all, when it was connected to A, current was rising, transient state. The entire sum is in the transient state, right? Not the initial, not to the steady, right? When A was connected to C, current was rising. It was as because of the mathematical expression I is equal to I0 1 minus e to the power TR by L. We have seen. Now, suddenly it went on to the maximum value, or it was about to reach to the maximum value. Suddenly this was disconnected and finally the connection between B and C was made. Source is removed. It means now decay of current will occur. Right? Decay of current will occur. In the decay of the current, right? If I'm talking about the circuit when it is connected, right? This is R, this is L. If applying the KVL to this circuit, we are going to reach up the solution, right? On applying KVL to the circuit. On applying KVL to the circuit. Now what happens? Voltage across the R plus voltage across the L is going to be 0. VR, it is going to be negative of VL. VR by VL, it is going to be negative of 1. A will be the perfect answer for this specific question. A will be the perfect answer for this specific question. Yes or no, guys? A will be the perfect answer for this specific question. Right? Can we move forward to the next one? Again, the same sum came on the LR circuit, but this time, right, it is going to be awesome. Again, this question is asked in JEE Main 2015. Okay. An inductor L is equal to 0.03 Henry, resistor is equal to 0.15 kilo ohm is connected into the series with the battery of 15 volt EMF. The K1 is kept closed for the long time, and then at t is equal to 0, K1 is open and K2 is closed. So at t is equal to 1 millisecond, the current into the circuit will be what? See, mark my words, what does this question states? First, K1 was open and K2 was closed. Sorry, K1 was closed first. K1 has been kept closed for very long amount of the time. If K1 is kept closed for the very long amount of the time, then I must say the circuit is in what state? Transient state. Current is rising. Rising. Now, when it was about to reach at the maximum position, immediately K1 was open and K2 was closed. Now, current will decay. Right? So, if the decay of the current is moving on, okay. See, all of those sums that we have seen, you can just check it out, right? Whatever the number of the sums we have seen, you can just check it out. It is only from the right the notes we have done. Okay, so the reason of right discussing all of those stuffs with the PYQ is that If I'm going to discuss that separately, then there is a possibility you might get leaved it. But the discussing all of those stuffs, right, with the PYQs is going to help you all remember all of those stuff for the very long amount of the time. Okay, now, first of all, let's have the 1 minute. Let's give you all a 1 minute to solve. Right, now see what happens. Current is decaying. If the current is decaying, then which equation we need to follow, right? Okay, if the current is decaying, then which equation we need to follow? I is equal to I0 e raised to minus t r by L, right? Suddenly, right, when K1 was open, see, when K1 was closed and K2 was open, the current has been rising to its maximum value. Now suddenly at t is equal to 0, when it was kept open and K2 was closed, it means that in entire circuit only L and R are connected like this way, right? This is of 0.03 Henry and this is of 0.15 kilo ohm, right? Okay, so it means that now current is getting decayed. Okay, so I is equal to, now I don't think so what happened here. Okay, finally we are onto the same point. So I is equal to I0 e raised to minus t, right? Time they are saying 1 millisecond, so it is 10 to the power minus 3. Resistance is 0.15, right, into 10 to the power 3, it's in kilo ohm, and the inductance is 0.03. So here we are going to get I is equal to I0 e raised to minus 5, right? I is equal to I0 e raised to minus 5. So can I say I is equal to I0 by e to the power 5? In the question it is mentioned e to the power 5 is 150, right? So can I write it as I is equal to I0 whole divided by 150? Can I consider this is equation number 1? Yes. Now, how you are going to calculate the value of the I0? I0 was that current, right, that was flowing into the circuit, right? Okay, when inductor is offering zero resistance, it means only resistor is connected. Okay, so I is equal to I0 whole divided by 150. Can I replace it at I0 as V0 by R into 150? Right, V0 is 15 volt, R is 0.15 into 10 to the power 3 into 1 of 50. So replacing all of those, 0.67 milliampere is going to be the perfect answer for this specific question. Right, 0.67 milliampere is going to be the perfect answer for this specific question. Right, the D is going to be the perfect answer. Right, the D is going to be the perfect answer for this specific question. Yes or no, guys? Okay, so this is how the questions from the LR circuit are right coming up into an examination. And moving aside, on the countdown of 5 to 10 seconds, if you want to just pause this video and note down the stuff, you can. Come on. Okay, I think that much time is enough. Let's move on to the next question. Aha, sir. Question that was asked in EIEEE 2002. Nah, very easy question. The effective inductance between A and B, A and D will be what? Right? Okay. I don't think so. We are going to give much time on that, but still, it is important, right, to give you all a minute. Moving aside, it is quite easy. You can just solve this stuff and answer it immediately. The inductance between A and D will be what? Right? Inductance. So let's redraw this circuit first. Okay, this is a D point, right? And this one is going on as an A point, and another we are having this kind of situation, right? All of those three inductors, right, are having the value of the 3 Henry. It reminds me about a method that we have discussed into the current electricity chapter. The complex circuits can be solved using the potential division formula. What does it states? Suppose we are going to start from this here, the potential we are going to get it as VA. Are we having any kind of the circuit element at this point? No. Potential is VA. Are we having any circuit element? No. Potential is VA. Are we having any kind of the circuit element? No. Potential is VA. Starting from the next, right? That is a D. Here the potential is BD. Are we having any kind of the circuit element? But we don't need that, right? We don't need that, because here suppose if it is connected also now, then it is DD, VD and VD. So if I'm talking about the three inductors, right? If I am talking about the three inductors, the first inductor, right, it is having the potential difference VAVD. The second inductor, it is having the potential difference of VAD, right? The third inductor, okay, it is having the potential difference of VAD. So three of them are having the same potential difference. It means that three of them are connected in parallel. If three of them are having the same potential difference, it means that they are connected into the parallel. So whenever they are connected into the parallel, the simplest thing that I want to represent, 1 by L equivalent, that is equal to 1 by L1 plus 1 by L2 plus dot 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 plus 1 by L of N. So here the L equivalent is going to be 1 Henry. L equivalent is going to be 1 Henry. L equivalent is going to be 1 Henry. Okay. Now, again a question from EIEEE 2002. Okay. You are saying, sir, it has been too long that EIEEE has been discarded. It's not like that. Okay. We are interested into the questions. The number of the questions that are cool, I am keeping in front. Okay. Now, this question will be completely based on the motional EMF. Okay, now let's move on to what does this question states. A conducting square loop of side L and resistance R moves in its place with the uniform velocity perpendicular to one of its sides. You can see into this question the cross are given. It means the magnetic field is directed inside. All of those cross are given. It means that magnetic field is directed inside. Okay, and the entire loop is moving like this way. So I told you all, just check it out whether the velocity is perpendicular to the magnetic field or not. Velocity is like this way. Sorry, magnetic field is like this way and velocity is like this way. So it means that yes, for sure they both are perpendicular, and yes, we are going to have the EMF within it. Why? Because the flux is also changing. Why the flux is changing? Because the area of the loop inside the magnetic field is getting changed. Right? Is getting changed. Yes or no? Right? It is getting changed. So, lots of data is given. The induced EMF will be what? The induced EMF into the loop. First of all, the explanation, right? Okay, whether according to the Faraday's law, the EMF is going to get induced or not. A great question in front. But first of all, I'm going to give you all a minute to solve this stuff. Okay. See now, the induced EMF, right? Induced EMF. Then how we are going to discuss that sub? See, first of all, we need to check it out whether the EMF is actually getting induced or not, right? So for that, I need to take out one example. Okay, and for that example, I have to draw lots of crosses here. Right? Okay. Now, at t is equal to 0, suppose the loop is at this position, right? The area of the loop inside the magnetic field is A. Now it is moving this side with the velocity v. After some amount of the time, right? The loop will be at this position, and then loop will be at this position, and then the loop will be at this position. Now, if I'm talking about the time t is equal to t of 3, here the area inside the magnetic field of the loop was A, right? But here half of the loop is inside the magnetic field and half of the loop is outside the magnetic field. It means the area of the loop is getting changed. Again, it is moving with the velocity v. Then after a small amount of the time, obviously it is going to leave the entire magnetic field area. So it means that according to the Faraday's law, if somehow the flux is getting changed, EMF is getting induced. Somehow if the flux is getting changed, the EMF is getting induced. The reason of having an induced EMF is only one, and that is flux needs to be changed. But the reason behind of having a change in flux is R3. Magnetic field can change, area may get changed, angle between the magnetic field and area may get changed. So here the area is getting changed. Okay, so one thing is sure, right? Area is changing, flux will change. Flux will change, EMF will be induced. Now what does induced EMF? E is equal to BVL effective for a loop, right? The L effective will be the one of the length of the loop, L. So here it is going to be nothing else but the EMF that is induced will be BVL, right? It is as because of the motion of the loop inside the magnetic field leaving that area, right? So it is nothing else but the motional EMF, right? Motional EMF. Okay, so here the D will be the perfect answer for this specific question. Okay, D will be the perfect answer for this specific question, right? Let's move on to the next question onto it. Two coils are placed close to each other. Two coils are placed close to each other. The mutual inductance of the pair of the coil depends on the mutual inductance of the pair of the coil depends on the current into the two coils, the rates at which currents are changing, the relative position and the orientation of the two coils, the material of the coils. Boom. Okay, see, first of all, if I'm talking about, let's understand the situation, the two coils are placed with near to each other, right? What will be the formula of the mutual inductance? The formula of the mutual inductance, right, that is equal to flux by current, right? Okay, or this you can say it as mu 0 n1 n2 area whole divided by the value of the current. Okay, basically if I'm talking about on what factor the mutual inductance depends, see, one coil is having, right, the change into the value of the current. On basis of that, right, one EMF is induced. So here what the scenario is, it's all about, as because of one mutually in EMF is induced in second, as because of one, mutually EMF is induced into the second, right? So it depends on second. My friend is going to come, I want to go out the film, yaar, come on, yaar, pack this stuff, or you are studying all of those time. So it depends on me. Choices are, choices mine, whether I want to go with them or not, right? So the choice of the second coil, right? Whether I want to introduce a self-induced EMF into the the mutual EMF into the myself or not, it depends on the type of the material, whether it is allowing or not. Things completely depends on when things moves on or not. I want to do it, don't want to move on. Chal bhag be, like that. Bhag, 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 pura din picture, padhai padhai kar. Sapet maro sapet. Right? This, all of those three reasons, right, are one of the reasons for the EMF, for the mutual EMF to get induced into the upcoming, the nearby coil. But it is important whether this coil is allowing or not. A material wouldn't be the conductor, right? Okay, then what you are going to do? If it is a good in resisting the current, right? If it is a good insulator, then what you are going to do? So it completely depends on the material of the wire. Or suppose if it is not an insulator, or the material, right, has been made with a higher resistance value, then what we are going to do? EMF will be induced. Most of the three things are going to get satisfied. But suppose in the nearby coil, right, its resistance value, okay, the material with which it is made is having the higher resistance value, then what we are going to do? Tunak tunak tara tara, right? So D is going to be the perfect answer for this specific question. Okay. This question is asked in AIEEE 2003. Okay. Now let's move on to wherever they have gone. Next question. When the current changes from plus 2 ampere to minus 2 ampere, when the current changes from plus 2 ampere to minus 2 ampere in 0.05 seconds, current changes from plus 2 ampere to minus 2 ampere, the current is decaying, okay. EMF of 8 volt is induced into the coil. The coefficient of self inductance of the coil will be what? AIEEE 2003. The coefficient of the self inductance of the coil will be what? Right? The coefficient of the self inductance of the coil will be what? Okay, let's give you all a 1 minute to solve this question. See, what does this question states? Right? What does this question states? It is important, right, to understand. See, the current value is changing from plus 2 ampere, right, okay, to minus 2 ampere. Current value is changing from plus 2 ampere to minus 2 ampere into the time span of 0.05 seconds, into the time span of 0.05 seconds. Now, as because of this change into the current into the this much amount of the time, we are having the self-induced EMF of 8 volt. We are having the self-induced EMF of the 8 volt, right? So can I say that the self-induced EMF, right? Okay, can I say it is L di by dt, right? L di by dt. Now, what happens here? We need to calculate the self-inductance of the coil. So the self-inductance, see, this is for the very small change. But you can just see out this data. We are having the change of approximately 4 ampere within this very small amount of the time, right? So for the very small change, the formula is mentioned like this way. For the very large change, right, the formula is like this way, delta I by delta T. So self-inductance of the coil is E delta T whole divided by delta I, right? The induced EMF is 8 volt into 0.05 seconds. The change into the current is 4 ampere, right? So it is 0.1 Henry, right? The self-inductance of the coil is approximately 0.1 Henry. The A is the perfect answer for this specific question, right? The A is the perfect answer for this specific question. Is it clear, guys? I'm moving aside. You have to just note this down. You can note this. So, okay, whether it is actually it is nothing to note down, but some students are sir, reh gaya. Okay, I think that much is enough. An ideal coil of 10 Henry is connected in series with the resistance of 5 ohm, battery of 5 volt. 2 seconds after which it is connected, the current flowing into the circuit. See, this question is asked in 2007, but it is asking 2 seconds after. 2 seconds after, at t is equal to 0 initial state, t is equal to infinity. This is steady state, right? This is initial state, right? They are asking at t is equal to 2 seconds. It means it is a transient state. And in this state, right, the battery is connected. It means the rise of the current is taking place. Okay. So which formula we are going to use? I is equal to I0 1 minus e raised to minus tr by L. Right. So guys, this is the homework from my side. You have to, everything is solved. You have to just answer within the video. Right. You have to answer beneath the video. Now, 2 coaxial solenoids are made by winding a thin insulated wire, right? The data about the 2 solenoids are given. One is having the area of this and length is this. Okay, one has this turns and second is having the 400 turns. Okay, then what will be the mutual inductance? Again, the formula used in this, M is equal to mu 0. This thing we have seen, number of turns into A whole divided by I. Right? Okay. So again, I'm going to give you all this question as the homework. Right? So this time I've given you all the 2 questions as the homework. So I'll be waiting for all of your comments regarding all of those questions beneath the video. Right? So students, it was all from my side into the electromagnetic induction, and soon we are going to come with the this one, what we can say, alternating current. Right? So hope so you like this lecture. Okay, now it's time to go. Right? So this is your own physics educator Indrajit Singh signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic, and take care. Bye everyone.